lab speed projectile motion. Okay, the introduction is we applied Newton's second law to a real world scenario and observed the effects of drag and gravity on a paper object, which is the paper ball, while it's falling using the program tracker. Then we used information such as the initial position and initial velocity to make two different computer models to look at the different forces. So the first computer model we found was one with no drag and just gravity. Then the other one was drag and gravity. And here are the concepts or formulas. So we obviously used the concept of Newton's second law of momentum. On the right, there is the position update formula and the velocity update formula, which we use in our code to find. And then there's also the other formulas we use, which is F drag, which is B times velocity squared, and F net, which is gravity plus drag, which we use these in our procedure. So the first procedure was this, which is the tracker. We threw the ball and made a video using the tracker to find the observed motion, and we plotted this in a graph, which is on the right. This is how we did the first part. After taking the video, we did this. Then we used that information, such as the initial velocity and the initial position, to plug into glow script. We also added the two formulas that I showed before, the position update and the velocity update, to then find a prediction motion of the one on the left, which is no drag, and the one on the right, which is drag. And then we put these all on a graph. So on the first graph, which is on this graph, it shows the trajectory of both the tracker, the no drag, and the drag. And you see in this, you can see that they all start in the same position, but obviously our tracker X value is way less. The final X value is way less than the final X value of the non-drag and the predicted drag, or either predicted ones, but the Y values are the same. This comes to my observation. I came to observation. Our experiment does not match the predicted motion. Now, our Y values match, but our X values do not match. And I do think this either could be a human error during the experiment, or a human error while using tracker, or also that we did not apply drag to the x-axis. So the x-axis was not impacted by anything such as drag or anything like that. Only the y-axis was impacted by drag. So it shows that like I said, the observed y position is similar to the predicted, but the x-axis is completely different. This is because x-axis in the predicted had no drag, but in actual real-world scenarios, it did have drag. So our y would be similar, but our x was not because of that. What does it mean? So if you're asking about terminal velocity when a free-falling object is experienced with no zero net force, examine the velocity time graphs predicted by your models with and without drag. Do any of your models predict a terminal velocity? If the answer is no, what similar experiments could you design to find terminal velocity? Discuss briefly. Right here is the velocity. It shows that with drag, without drag, the y component was linear, but with drag, the y component was more flattens out. So it was exponentially decreasing. So it started high, the exponentially increased and then flattened out. And while it would nod, it did not do that. It was linear, which is on the left. Right. What if? Imagine if you throw straight out with the same initial speed in your experiments, would the time this object take to reach the ground would be the same, longer, short? Okay. It would be longer. This is because the initial position it would take longer for the velocity of the y value to be negative, because in the initial in our experiments, the y value starts at 0 and the x value is positive. But if you start the y values positive, that means that the gravity would have to overtake the the y value and velocity, meaning that it would take longer for it to reach the ground because the velocity y value would start positive, and gravity would have to cancel that out, which meaning that it would take longer to reach the ground, to reach the floor. Thank you.